All right, we're back. Let's talk now a little bit about the types of reactions that we can perform with aldehydes and ketones. First, of course, we do need to talk a little bit about the difference in reactivity of these molecules. Um, Now, whereas the ketone has two alkyls bound to the carbonyl carbon, an aldehyde does not. At best, an aldehyde will have only one alkyl bound to that carbonyl carbon, but the other substituent attached to the carbonyl carbon is just a hydrogen. So reactivity-wise, what we see is that the aldehydes are more reactive than ketones. And the main reason for that is because the aldehydes, by not having a second alkyl bound to the carbonyl carbon, makes it so that the attack on the carbonyl carbon or the carbonyl component is more likely because you have a lot more room available for nucleophiles to come by and interact with the carbonyl. Whereas in a ketone, the presence of the two alkyl groups presents a little bit more steric hindrance and a little bit more complication to attach to that carbonyl carbon or have a nucleophile incoming to try to interact with the carbonyl carbon. Another thing as well is that because of the presence of the two alkyls on the ketone, there is hyperconjugation that does donate electron density to that carbon. And because there is that additional electron donation to the carbon, that means that the carbon is not as electrophilic as it could be. So that also lowers the reward, if you will, from the point of view of the nucleophile to attack a ketone as opposed to an aldehyde. So all in all, aldehydes are a lot more reactive than ketones. So with that in mind, let's take a look at nucleophilic addition reactions. So what basically happens is that the nucleophile attacks the carbonyl carbon of your carbonyl molecule. So in this case, we have an aldehyde. We have 3-methyl butanal. And if you bring this in contact with water, one thing that can happen is that the water oxygen atom can attack the carbonyl carbon. And in doing so, the pi bond of electrons has to break and move over to the oxygen, or what used to be the carbonyl oxygen. Now, what that basically creates is a situation like this, where now you have two oxygens bound to the same carbon. Initially, you have negative and positive formal charges. So usually what happens here is that there's a proton reshuffle to lower the formal charges in the molecule. So first you deprotonate the molecule, and basically another molecule of water can do the trick. Just have that water molecule, that second water molecule, remove the proton from the oxonium cation. That moves the electrons of that OH bond directly to the oxygen, making that oxygen neutral. And the hydronium that you've generated in this process is now basically situated perfectly to give that proton back to the actual oxide atom that you see right there. So here's the protonation event. So basically that attacks the proton. The electrons go back to the oxygen, reforming the water that you started with at the beginning. But notice what's happened right here. In this event, you have created a molecule that used to have a carbon-oxygen double bond, and you've traded that for two carbon-oxygen single bonds. In essence, you still have the same quantity of carbon-oxygen connections or binding modes, but the actual type of bond is what's changed. You traded a double bond for two single bonds, but they still happen to be carbon-oxygen connections. All right, so that's one thing. Now, this thing, being that you have the two alcohol units bound to the same carbon, you have a specific name for them. We tend to refer to them as gem diols. And the gem prefix emphasizes that the two alcohols are bound to the same carbon. All right, so that's kind of the idea. Now, the other thing to also keep in mind is that this is an equilibrium. When you have a mixture of water with your aldehyde, you do form the gem diol, but this will still remain an equilibrium. So you could easily bring it back to the pure aldehyde under the right conditions. And you can use the Chatelier's principle to go favor the product as opposed to the reactants or vice versa. So speaking of that, one last thing to mention is that due to the fact that you have two groups with plenty of lone pairs on the same carbon, those lone pairs do repel each other a little bit from group to group. So the gem diol is not as favor as the aldehyde, but you still form, a fair amount of it in solution anyway. Um, all right, now as far as the reaction is concerned, that only took place under neutral conditions. It was just water. But you could do the same thing and even so more efficiently by adding a little bit of acid. And you don't need a lot. You just need maybe a drop for, a 10 ml, 15 ml, 20, 50 ml solution. All it takes is one, maybe two drops of acid, and all of a sudden the acid itself will serve as a catalyst. So the difference here is that now your acid, which I'm basically treating as if this is HCl in aqueous solution. So hydronium is the form which HCl will take place. Um, Hydronium protonates your carbonyl oxygen. That's the first thing that happens under acidic conditions. And as you will see throughout the mechanism, one thing that has to remain constant is that if you undergo a reaction under acidic conditions, all your intermediates have to be either neutral or have a positive charge, like we see here for hydronium. And as you'll see later, if we do things under basic conditions, then everything has to be neutral or negatively charged from the point of view of the substrates. All right, so we protonate the carbonyl. The electrons of that OH bond move over to the oxygen, and we end up with a protonated carbonyl as well as water. And then one thing to highlight right here is that the protonate carbonyl has a resonance structure, meaning that the carbon down here is electrophilic, uh, quite a bit, as a matter of fact. In essence, this is kind of like a method of activating the nucleophilic reaction that's about to happen, because now you made that carbonyl even more appetizing to a nucleophile. So the nucleophile comes in at this point and says what's going on with that carbonyl carbon, and water says, yeah, I have to get me a piece of that. And so the water attacks the carbon. We get the pi electrons moving over to the oxygen, the oxonium, making it neutral, right? Now, but the water with the two hydrogens is now got a positive formal charge. So basically, the water that you generated in the previous steps comes along and removes that proton to give you the neutral gem diol. And in the process, you have reformed the hydronium that was used at the very beginning. And that basically satisfies the idea of being a catalyst. You get used initially, but you get reformed later on. So you never actually get consumed. And that's the reason why you don't need much quantity of it at all, because it's getting reformed throughout the entire process. All right, so that was the big thing, right? So the catalyst is reformed in the last step. And like I mentioned earlier, under acidic conditions, all the intermediates, as you probably already noticed, were either neutral or they have a positive charge. That's very important. If you end up generating negative charges for your organic substrates, you're probably generating something that is strongly basic, and you cannot have a strong base if the conditions are acidic. All right, so to kind of follow that same train of thought, you could perform the same reaction under basic conditions. So this time around, you wouldn't be adding a little bit of HCl. Quite the opposite. You'll be adding a little bit of like sodium hydroxide, a strong base. And so under that premise, you will have some hydroxide present in solution. And once again, it's going to act as a catalyst, so you don't need a lot of it. But it will act as a catalyst, first by reacting, and then hydroxide is a much better nucleophile than just regular water. So the first event is literally just a nucleophilic addition onto the carbonyl carbon, which will break the carbonyl double bond, push the electrons towards the oxygen. And notice that in the process, now we have a negative formal charge on that oxide, right? So we're now generating negatively charged particles. All right, what happens right there is that now you have to protonate that oxide. And the way you do it is just with water that has to be present, because sodium hydroxide is going to be dissolved in aqueous solution, right? AKA water. So the alkoxide will attack the proton, Those electrons will go to the oxygen, and in the process, you will reform the hydroxide that we used in the first step. So this is a little bit more to the point. 2 steps, finito, everything is done. But every step of the way, you can see that all the organic substrates are either neutral, as in the case of the reactant or the final product, or they're negatively charged, as in the case of the intermediate. So yes, we have reformed the base, which means that yes, it is a catalyst, but the basic conditions have to be done such that your intermediates and your products, reactants, are neutral or negatively charged. Okay, so with all that information that we've just covered in terms of regular nucleophilic additions, in the next video, we're going to then go in depth as to all the different oxygen types of nucleophiles that we can use. And from there, we'll go on to other elements as well that can act as nucleophiles. Okay, so see you in the next video.